Hello, it's Keith here, and this is lesson 76 of the platform-specific series of my 650 assembly programming tutorials. We're back on the Atari 2600 today, and we're looking at the sprites. Now, the Atari 2600 has hardware sprites as such, but they don't work like you might expect hardware sprites to do, because nothing does on the Atari 2600. What we've got today is we've got the example here. You can see we can move our little sprite around the screen. The sprite, as we're sort of considering it today, is this sort of square object. Now you'll see that there's a vertical line reaching the top and the bottom of the screen here, and there's a good reason for that. You see, the sprite actually works the same as the playfield in the sense that we have a single 1-byte register which defines the bitmap data for our sprite, and that is drawn down the entire height of the screen. And the only reason that it changes and we've got that kind of square object in the middle there is because I'm timing things, calculating the number of lines and changing the bitmap data for the height of the sprite, the 16 pixels that I've defined to be the object, and then we're switching back to that line. Now the line is actually just there to make it clear what's going on. If I was going to write this as a proper game and that was maybe the targeting cursor for our character or something, for our player or something, what I would actually do is I would replace that line with just blank, and then you would end up with something like this. But that doesn't make it so clear what's actually going on behind the scenes, and I think it is important to work out what is going on behind the scenes. Now the Y coordinate is basically defined by the point that we actually change to the bitmap data we want to show. The X coordinate is different. Basically it's set in two different ways, and we have to use both. Now the first way is that we can send a command to the hardware that will time the X position of the hardware sprite to match the current raster position, that the raster being the drawing of the image on the screen from left to right. So basically we count down a timer and then we run this command, and the X position will be set to the raster beam. However, that is not pixel perfect. It's only approximately around 16 pixels accurate, and we then need to use a move command to do a shift to actually correct to the pixel perfect position that we want. And it's the combination of those two that is producing the result you can see today, which is some pretty reasonably smooth movement on the X and Y axis. I think this is pretty good. I don't know if it's perfect, but it's pretty good, and it's good enough. So that's what we're going to look at today. Now, if you go to my website on the Atari 2600 page, we have a list of all of the registers relating to sprites here. There's a wide variety of them. We have scale registers, this number and size. We will see some examples of that in a moment. We've got colors. We can set the color for the sprite and the missile. The missile is a single pixel object. Think of the ball within Pong. The Atari 2600 is basically a Pong console that's been a bit upgraded. We have the resets. These set the X position. We have the graphics. This is the bitmap data that we are passing that is going to be drawn to the screen. We have the horizontal motion. This is for the tweak, as I call it, tweaking the position. Once we've set the crude position with that reset to the raster beam position, we then tweak it via this move. We've got vertical delays. I'm not using these, but these are basically, I believe these allow you to set both sprites simultaneously. So you can say, well, don't set the bitmap data for a sprite for player 1 sprite until player 0 sprite's done, and vice versa. I've not used those, but it's something like that. And we have the H move, which we will need. This is where we write to this address, and that will actually apply the tweak. Now we have to do that after a W sync, otherwise it won't work properly. So we initialize the move that we're going to want to make with the HMP in advance, and then we do the H move after the fact. Okay, anyway, let's go over to our code and let's take a look at what we've got. So here's the example code today. It's this A26 sprite here. We're using 2 bytes for the 0 page for X and Y position. So at the start, we are basically setting things up. We are setting up the color for our playfield background here with the register 9 there. And then we are setting the starting X and Y position of our sprite. Now what we've got next is a bit fun. We are setting the number and size register for player 0, the first player, and that is register 4 here. And we're writing a value of 0 here, but let's try writing some other values because we'll get some interesting things. Now you see, the sprite has to be 8 pixels wide, and there can only be one hardware sprite for the player. However, we can do some rather weird things. You see, depending on the value that we give this parameter, we can actually make that sprite double width or quadruple width, and we can also make it repeat. Now, we've got basically the values 0, 5, and 7 here. If I just change this to an integer just for simplicity here, and if I put in a 5 here and run again, well, now you'll see that the sprite is actually a bit chunky. It's double the width. And if we change it to 7, you'll find Well, it's now quadruple the width, so we can actually make it wider. It's still only 8 pixels, it's still only 8 bits wide, so it's not got any higher in resolution, but it's got wider in screen space. As well as that, we can actually double the sprites, so it will appear twice. So now we have 2 sprites, and we can actually double the number of sprites, and we can space them out a bit more by setting this to 2. You can see now they are further apart, and we can change that to 4 as well. And then it will be even further apart. Still, and I think this is used for your Space Invaders type game. I think they're using the player sprites to do all of the enemies in the background, and then they're just spacing them out and things. I think basically, we can even have 3 sprites. We can't have 6, but we can have 3. So there are 3 sprites in a line there, and they will all move in tandem. Of course, all of these will work in tandem. And we can have 6 as well, and that's the final option, and that is spacing them out further. So even though the hardware sprites are quite limited, if you design your game correctly, as I say, think Space Invaders, where the enemies always move in tandem and they're always spaced out in very nice even positions, that is perfectly suited to that. So that's one thing that we can do there. Now, that's the initialization. Then we've got some code to do our VSync. I covered all of this in the first example with the play field, so please take a look at that if you need to know what this does. Basically, this is timing the VBlank, so starting the drawing of the screen. We've got the do game tasks routine here, which is where we're going to do our calculation, reading the joystick, calculating the new position for the sprite, things like that. So let's take a look at that right now. Okay, so here's do game tasks. We're loading the X and Y registers with XPOS and YPOS. Now we're going to use these later on to reset the player if the player's gone out of bounds. So what we're then going to do is we're going to read in up, down, left and right of the first joystick, joystick zeros. So those are in the top nibble of the register at memory address 0 to 80. So we're reading that in, and we're testing bits 4, 5, 6 and 7, and we're changing the YPOS and XPOS, which will be the final position of our sprite according to those bits. Now a value of 1 in those bits is not pressed, and a value of 0 is pressed, so we're branching if non-zero when we're doing our tests here, because if there's a 0 the button is pressed down, and so we're going to move up or down the screen as required. Now once we've done those moves, we're then going to check the position of the sprite. We don't want the sprite to go off the edges of the screen. Now if they go below 0, it will wrap around back to 255. Minus 1 is 255 in unsigned numbers. So we're actually only checking one boundary each time here, and that will do the job. So we're checking if our XPOS is over the boundary here, and we're resetting the X position. If it is, then we're checking the Y position and resetting it if it is. 16 is the height in pixels, and 8 is the width in pixels as well for this sprite. You'd need to change those if you're using double width and things like that. Now the final thing we're going to do is we're going to check the fire. I didn't actually show the fire, I forgot about that. If we use the fire button, we're actually changing the color of the sprite. So if I move around a bit and I press fire, you can see it goes brighter blue. So that's what we're doing here. We are checking the fire button here, and it's memory address 3C has the fire state, the top bit. And so a -1 value there is the fire's not pressed, and so we're skipping over that load there. So we're using the value 88 for the normal color, and if the fire is pressed, we're using 8F. The top 8 is the color, and the bottom 8 or F is the brightness. So that's how this works. If I change this to a 9 and I change this to a 9, we'll get a slightly different color blue. Maybe it'll become more purple or more green. It's become slightly more green there. So yeah, we can change the color and get to different values there. So there we go. That's what that code is doing, and we set the player color with register 6 here and color player 0 there. Okay, so we've now set up our color and we've decided the next X and Y position. We now are going to process the X position because we need to do this at very, very precise timing, and it doesn't matter when during the screen we do it. We can do it while VBlank is occurring. So that's what we're going to do now. Now what we're going to do is we're going to take the bottom 4 bits of the X position here, and then we are going to basically use this via a lookup table to calculate the offset. Now the offsets are a little bit backwards, so it uses the top nibble here, and a value of 7 in the top nibble is a shift to the left. A value of -8 in the top nibble is a shift to the right. So kind of backwards there, and a value here of 0 will actually be a no shift at all, so just keeping the position constant there. So those are the values, and I'm using a lookup table to calculate those. That was what was working best for me. So that's what we're doing there. We're getting the lookup value there offset according to the bottom 4 bits within the X position there, and then we are going to store that to register memory address 20 there, and that is the horizontal motion for player player 0 there. And now that is defined it, but it's not applied it yet. We're going to apply it in just a moment. Okay, so we've basically taken the bottom 4 bits of the X position there. Now we're going to take the remaining bits. So we're loading the X position here, and we're basically dividing by 16 here. And this is a delay loop here. So we did our W sync up here. So this was a W sync here. So that has basically synchronized to the edge of the screen. There was a little bit of time till we got to the left-hand side of the screen, which is why we did our calculations here. That was using up a little bit of time there. And then what we're doing here is we are now waiting, and we're basically counting along the screen the raster beam. And once our count goes below 0 here, as we're subtracting 16 repeatedly, we're now in the position we want to be, and we're then going to synchronize the X position of our sprite to the current raster beam position. And we do that by writing any value to memory address 10. That is the reset player. Reset resets it to the current raster beam position. So that's what we're doing there. So now we've got our approximate X position. Now if that's all we do, we will get very, very crude positioning. If I run this again with the remaining commands removed, with that tweak removed, so to speak, well, we are now only able to move in very large chunks, which probably isn't what we want to do. So we need to do the remainder by using that move that we defined up here via that lookup table. We need to do another W sync. That's what we're doing when we're writing any value to register 2 there. And then we are basically doing the horizontal move by writing any value to 2A. Now this applies the move that we defined up here. Now that we've achieved our crude positioning with this part here, we're now doing our fine positioning here, and that sets the X position of the sprite correctly. Okay, that's our X position ready. As I said before, our Y position is all done with our bitmap data. Our sprite is defined by the 16 lines here. Now the height of your sprite, the width always has to be 8 pixels or 8 units, depending on if it's doubled, I suppose you could count those still as different resolutions of pixels. But the height is always going to be, but the height can be anything we want. It could be 192 lines. You just need to have 192 bytes of data. Or we could have just 4 bytes and we could repeat them for multiple lines. It just depends how we read in the data from this source data here, and how we set the bitmap data register, the graphics player 0 here. These 8 bits there define the pixel data, and it's only when we change those that the drawn data to the screen will change as well, just like with the play field. So what we're going to do during our main loop here, this is after we've done our do game tasks, we are then going to start counting the lines of the screen and change the bitmap data. Now we've got 2 pieces of code that do. Now we've got 2 registers we use here. The Y register is counting the scan line of the screen, so 0 to 191 there for the line of the screen. The X register I'm using for the line of the sprite. So until we get to our Y position, that is going to stay at 0, and then once we start ticking past the Y position of our sprite, we will start reading in the bitmap data until we get to the last line, line 16, and then we're going to switch off again, and that's what this code's going to do. So the way I've coded this, you could do it other ways, but the way I've coded it is I'm loading the default value here into the accumulator, and that is provisionally going to be the line that we're going to draw into the sprite. However, we then compare to the Y position of our sprite. If we're lower, we're just going to skip over and write that data into the sprite register here at 1B, which is GRP0, and that sets the bitmap data being shown by the sprite. The store 02 there is a W sync, so we're just synchronizing to the left hand side of the screen again there. We need to do that anyway at some point, and this is a nice clean place to do it. So if nothing else happens, we would draw that line to the screen, and that's why you saw that line going all the way down the screen in our example here. So before and after that is what is drawn to the screen, but in the middle we're loading data from our sprite. Now if we are below the top of our sprite, we're then checking if we are below the bottom of our sprite. Our sprite is 16 tall, so we're comparing the line of our sprite in X to 16. If we're below that, then we're actually in the middle of our sprite somewhere, and we want to read in some sprite data, and that in that case is what we're doing. So that's loading in the bitmap data and drawing it to the screen. Now as I say, the sprite can be any height at all, so I can change this to 32 or even 6. Why not go for 64? Why not go for 191? where you can see we don't have any valid data there, so we're just starting to write bits of our lookup table and things. But as I say, the principle stands that this sprite, while it has to be 8 pixels wide, can be the entire height of the screen tall. And of course we have a second sprite for player 2 as well. So you know, despite the limitations, you know, there is some flexibility there. So once we've done a line of our sprite, we're just repeating, incrementing the Y counter and seeing if we've done the entire height of the screen. Once we have, we do the overscan area and we repeat. We just repeat infinitely until the player gets bored of this very simple example, but there we go. So that's all we've got today. As I say, go to the website, download the source code and the build scripts and have a play with it, and I'm sure you can have some fun with this. That's all I'm planning to do on the Atari 2600 at this time. If you've liked what you've seen, please leave a comment and I will think about doing some more. I cover lots of other systems in my tutorials, and to be honest, the Atari 2600 is a very different beast to the vast majority of them. Most of the systems I cover are either bitmap based screens or tile sprite based systems like the Master System. They're far more technically advanced than this system, which is very early, and as I say, is really just a step up or two from the Pong console. So I can't port my usual code to a system with these limitations, but if a lot of people are interested in it, I will come back and I will do some more, maybe cover the collision detection, or you know, the use of the missile, the ball kind of thing, and there are some other things I can do, but they aren't really in the direction I was planning to go with these tutorials. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.